When you look at the way we talk about artificial intelligence today, there is just this fascinating disconnect
Oh, absolutely. No.
because we use these incredibly ethereal, like almost spiritual terms to describe it, right?
Right.
We talk about neural networks and the cloud and large language models, generative algorithms. We basically picture AI as this, I don't know, this pure disembodied thought.
Like it's just floating out there.
Exactly, a sprawling ecosystem of mathematics just floating somewhere in the digital ether. But today, for this deep dive, we are grounding that conversation hard.
Yeah, we are dragging it right back down to earth.
We really are, because we're looking at this amazing July 21's 2026 article from Technology Review. And it argues that the future of AI, the real future, isn't going to be determined by some, brilliant new string of code.
No, it's not.
It's going to be determined by dirt, metal, and atomic structures.
Which is just a profound shift in perspective. I mean, for the last 2 decades, the tech industry has basically operated on this assumption that software is the ultimate frontier.
Right.
Like the code was the only constraint. If you could dream it, you could code it. But as this article highlights, we're currently reaching an inflection point. The sheer ambition of our software is colliding head-on with the physical boundaries of the periodic table.
Which sounds like sci-fi, but it's happening right now. And that's our mission for this deep dive with you today. We are exploring this wild intersection of AI and materials science. Because if you read the headlines, or, if you just follow the money, the focus is incredibly skewed right now.
Oh, completely skewed.
Billions of dollars are being poured into massive data centers, raw computing power, and designing ever more complex algorithms. We're treating AI like it's purely a mathematical puzzle. Okay, let's unpack this, because if we want to understand where artificial intelligence is actually heading, we have to stop looking at the software and start looking at the microscopic physical building blocks that allow that software to exist at all.
And, the current financial obsession with algorithms, it is entirely understandable. I mean, software is the interface, right?
Sure, it's what we see.
Exactly. It's the flashy, visible output that writes the essays for you or analyzes the medical data or generates those crazy images. But the premise here is that treating software as the primary driver of the AI boom, it ignores the fundamental reality of computation.
Which is what exactly?
Well, the evolution of physical materials is actually the only thing that enables these mathematical models to execute in the real world.
Let me try to contextualize this, because I was thinking about it earlier. It feels like we are standing on the sidewalk staring up at a 100-story skyscraper.
Okay, I like this.
And we are just completely captivated by the architectural design, right? Like the way the glass curves, the cool layout of the penthouse.
Right, the aesthetics.
Yeah, and that's the algorithm. That's the software. But while we're staring at the glass, we are completely ignoring the metallurgy of the steel girders or the chemical composition of the concrete down in the foundation.
The stuff that's actually doing the heavy lifting.
Exactly. The stuff that actually keeps the entire structure from collapsing under its own massive weight.
What's fascinating here is that we've reached a point where the architects, the software engineers in your analogy, they want to build a 1,000-story skyscraper now.
Right. They want AGI. They want the next massive leap.
Exactly. And the mathematics to do it are sound. The blueprints are ready. But if your fundamental building material is still just standard 20th century steel and concrete, that building is going to crush itself by the time you reach, like, the 200th floor.
It just structurally cannot hold.
It cannot hold. The limiting factor is no longer the design. It is the tensile strength of the material itself. And in the context of AI, that material is the semiconductor.
Which is such a wild realization when you consider how much we take Moore's law for granted.
Oh, we totally take it for granted.
Like, we just expect our devices to get infinitely faster and infinitely smaller every couple of years. It's just a given. But the Technology Review piece points out that AI systems are now demanding processing power and memory at a scale that is basically breaking our current physical infrastructure.
Yeah.
We are hitting a literal wall.
We absolutely are. And to understand why, we have to kind of zoom in and look at what computation actually is.
Yeah.
Because when an AI model, quote unquote, thinks, it is not performing magic.
Right.
It is physically moving electrons across microscopic silicon pathways. It is forcing electrical currents through gates that are now, in many cases, only a few atoms wide.
But wait, I have to push back on this premise for a second.
Sure.
Because if the problem is just that we need more power and more memory, why is it a material science problem? Like, why can't we just throw brute force at it?
Meaning what?
Well, you see these tech giants partnering with energy companies trying to reactivate literal nuclear power plants just to feed their new data centers. If you have infinite money, which these companies basically do, why not just build facilities that are 10 times larger using the exact same silicon chips we already have?
It's a very common argument.
Yeah.
And it makes logical sense on the surface. Like, if the brain isn't fast enough, just build a bigger brain, right?
Exactly. Just buy more chips.
But the problem with throwing brute force volume at our current material architecture is that you run headfirst into the unforgiving laws of thermodynamics and quantum mechanics.
Meaning what exactly? If I wire a million old chips together, I still have the processing power of a million chips.
You do, technically, but at an astronomical cost of efficiency and latency. Let's look at the actual mechanics of it. As you pack billions of transistors onto a standard silicon chip, and you run data through them at the insane speeds required for modern AI, those moving electrons generate heat.
Right, because of friction.
Basically, yeah. They encounter physical resistance from the material. So if you try to scale that up by just building a massive, sprawling warehouse of these standard chips, the physical distance the data has to travel literally becomes a bottleneck.
Ah, I see. So it's a density problem.
It is.
You can't just spread the brain out over 10 football fields because by the time one side of the data center talks to the other side, the AI model is just too slow to operate in real time.
Precisely. And even more fundamentally, you can't just keep shrinking the silicon pathways to pack them closer together to solve that distance problem.
Because they're already atom-sized.
Right. When a transistor gate gets down to the width of just a few atoms, electrons stop behaving predictably. They start quantum tunneling.
Wait, tunneling, like going through walls.
Basically hopping the fence and jumping through solid barriers. The material itself loses its ability to control the flow of information. So, no matter how brilliant your code is or how many billions of dollars you spend on data center real estate, the silicon simply cannot push the electrons fast enough or efficiently enough to handle the next generation of AI.
It's like trying to move a million people through a subway system, but the tunnels are only 3 feet wide.
That's a great way to put it.
It doesn't matter how well you organize the train schedule or the algorithm, the physical space is going to cause a catastrophic bottleneck.
That's a much more accurate way to look at it, yeah. We're trying to push an ocean of AI data through a garden hose made of standard silicon. To run the advanced artificial intelligence of the future, the hardware needs to be fundamentally reimagined at the atomic level.
Wow.
We don't just need more materials, we need entirely new materials. We need substrates that allow electrons to move with zero resistance, or materials that process information using entirely different physical mechanisms.
And this naturally transitions us into what is probably the most alarming part of this whole equation.
The energy.
Yes, because here's where it gets really interesting. The energy cost. We talked about tech companies buying up nuclear power, and we kind of touched on the heat issue just now. But the source material makes it incredibly clear that the energy consumption of these AI models is becoming a massive sustainability crisis.
It's staggering.
I've heard people compare running these new AI models on old hardware to strapping a state-of-the-art massive jet engine onto a regular 4-door sedan. Like, sure, it has incredible power, but it's going to literally melt the chassis.
The jet engine analogy is close, but I'd actually refine it a bit.
Okay, how so?
It's more like putting a massive jet engine inside a sealed concrete garage.
Oh, wow.
Yeah. It's not just that it burns through fuel at a terrifying rate. It's that the heat and exhaust have nowhere to go, and the entire system becomes dangerously unstable.
Yeah.
When we talk about the energy cost of AI, we aren't just talking about your electricity bill going up.
We are talking about grid collapse.
We are talking about an energy footprint that is physically unsustainable on a planetary level. Training a single massive AI model using current semiconductor materials requires gigawatt hours of electricity.
Just for one model.
Just for one.
Yeah.
If we want AI to integrate into our daily lives,
Yeah.
Managing our power grids, driving our cars, discovering new pharmaceuticals, and we try to do all of that using our current silicon infrastructure, the energy demand would rival that of entire industrialized nations.
Which brings us back to the materials. How exactly does a new chemical compound or a new metallic structure act as the solution to a global energy crisis? Like, how does material science fix the sealed garage problem?
Well, if we connect this to the bigger picture, you have to understand where that energy is actually going. In a traditional computer chip, a massive percentage of the electricity isn't actually used for computation at all.
Really? Where does it go?
It's lost as heat due to the physical resistance of the material, like we talked about.
Yeah.
And it's wasted by constantly shuttling data back and forth between the memory and the processor. It's highly, highly inefficient.
Oh, I see. It's like a delivery truck that has to drive all the way back to the warehouse for every single package it drops off instead of just loading them all up at once.
Exactly that. It's known as the von Neumann bottleneck. Now imagine a material scientist discovers a new compound that allows for what they call in-memory computing.
What's that?
It's a material where the data doesn't have to travel at all. The memory cell itself performs the calculation. Or imagine discovering a stable material that conducts electricity with near zero resistance at room temperature.
So the electrons just glide, no friction, no heat.
No friction, no heat, and a fraction of the electricity required to perform the exact same mathematical operation, or even stepping away from electrons entirely. What if we develop optical computing materials that process data using photons of light instead of electrical currents?
Light instead of electricity. That's
Yeah.
incredible.
Right. And these aren't just minor iterative upgrades. Finding ways to improve energy efficiency at the material level is the defining hurdle of this era. By discovering these sustainable technologies, material science isn't just improving AI, it is quite literally rescuing it from burning itself out.
It fundamentally changes the math of what is possible. Like, if a new material cuts the energy requirement by 90% because it doesn't generate heat, you don't need a nuclear power plant to run your data center.
Exactly.
You can suddenly build an AI system 10 times more powerful on the exact same power grid we have today.
And that is why the article positions these materials as the unsung heroes. Without these leaps in physical sustainability, the entire AI revolution hits a hard ceiling. The algorithms become too expensive, both financially and environmentally, to actually deploy in the real world.
This is such a wild paradigm shift when you really think about it.
really is.
Because culturally, we have spent the last 30 years deeply conditioned to believe that the future is written on a keyboard.
Oh, absolutely.
When you picture a tech visionary or a Silicon Valley innovator, you picture someone in a dark room with a code editor, typing away, creating the future out of pure logic and math.
The whole hacker aesthetic.
Right. But if the physical constraints and the energy efficiency of the hardware are the true bottlenecks, we are looking at a massive shift in where the future of technology is actually being created.
The technology review piece zeroes in on this exact cultural and professional pivot. We are seeing a groundbreaking shift away from pure software engineering as the sole driver of progress. The realization is that the next big AI breakthrough isn't going to come from someone tweaking an algorithm in a code editor. It is going to come from the lab bench.
So what does this all mean? I want you, the listener, to really visualize this shift. We are talking about a world where the most vital players in the artificial intelligence boom aren't computer scientists.
No, they aren't.
They are chemists. They are physicists. They are material scientists standing in physical laboratories, wearing safety goggles, synthesizing rare earth metals, and testing molecular lattices. It completely upends our stereotype of how technology advances.
This raises an important question about how we organize scientific progress. Historically, hardware and software have been treated as entirely separate silos.
Oh, totally. Two different worlds.
Right. You had the materials people who built the silicon wafers, and you had the computer scientists who wrote the code that ran on them. They rarely spoke each other's language. But this crisis of physical limitation is forcing an unprecedented convergence of disciplines.
Because the software engineers can't build a smarter AI until the chemists give them a better chip.
Precisely. But here's the most fascinating part of this entire dynamic. The chemists also can't discover that better chip without the AI.
Wait, really? Untack that for me. How does that work?
Okay, think about how material science traditionally works. It has historically been a field of trial and error. You mix elements, you synthesize a compound, you test its conductive properties, and you see if it works. It takes years, sometimes decades, to discover and commercialize a new material.
Which we don't have.
Right, we don't have decades.
Because the AI models are scaling so fast that they need the hardware today.
Exactly. So to speed up the discovery process, material scientists are now using current AI models to simulate millions of molecular combinations.
Oh, wow.
Instead of mixing physical chemicals in a beaker and hoping for the best. They're using complex neural networks to predict the quantum mechanics of entirely new theoretical materials. The AI basically looks at the periodic table and says, if you arrange these specific atoms in this exact crystalline structure, it should conduct electricity with zero heat.
That is unbelievable. So it's a massive self-sustaining feedback loop. The code editor is designing the lab experiment, and the lab bench is synthesizing the materials to build a better code editor.
It is the ultimate bootstrapping problem. The artificial intelligence is actively discovering the physical materials required to build the next generation of artificial intelligence.
That's just mind-blowing.
When the chemists take those AI-generated predictions, synthesize the new material on the lab bench, and prove that it works, that highly efficient material is then used to build a far more powerful AI, which, in turn, can simulate even more complex and efficient materials.
It's a snake eating its own tail, but it's spiraling upward instead of destroying itself. I love that so much.
It's an elegant solution.
It really is, and it fundamentally proves that innovation doesn't happen in a vacuum. You need the computer scientist's grasp of mathematical architecture, absolutely, but you combine that with the physicist's deep understanding of thermodynamics and the chemist's mastery of molecular bonds.
And the cross-pollination of those fields is what enriches our entire understanding of progress. It shows that multiple perspectives aren't just a nice idea, they are structurally essential to unlocking the next massive leap in human technology. The digital world was never truly separate from the physical one, but now they're actively designing each other.
It's poetic in a way. It takes this incredibly abstract, almost mystical technology of artificial intelligence and grounds it right back into the dirt.
It really does.
It reminds us that no matter how vast or complex our virtual worlds become, no matter how human our algorithms seem, they are forever anchored to the rocks, the metals, and the fundamental physics of the Earth.
The algorithm is only as capable as the physical material it runs on. We spent years assuming the software was the limit, but we finally realized the software is just the blueprint. The materials are what actually make the building stand.
Which brings us to the end of our deep dive today. We set out to dismantle the illusion of the intangible cloud, to look past the glowing screens and to find the unsung heroes of the artificial intelligence boom.
And I think we found them.
We did. And what we found is that the future of technology isn't just about writing smarter code. It's deeply, inextricably intertwined with the physical sciences. Finding new ways to manage heat, reduce energy consumption, and rethink the atomic structure of our hardware is actively driving the future of tech.
It is a critical reminder that society must continue to invest in the hard, physical sciences. The lab bench and the physical materials being tested there are just as vital to our digital future as any software company in Silicon Valley.
Absolutely. The future isn't just virtual, it's highly physical. And as we leave you today, we want to circle back to that jarring contrast we started with.
The ethereal versus the dirt.
Exactly. We talked about how easy it is to imagine AI as this ethereal thought cloud, totally detached from the real world. But now that we've dragged it back down into the dirt and explored the atomic limits of how computers actually think, I want to leave you with this one final thought. If the next great leap in artificial intelligence relies entirely on the physical materials we can discover on a lab bench, you have to wonder, will the ultimate limit to artificial intelligence be decided by the boundaries of human imagination and code, or by the finite physical properties of the Earth's elements?
That's the billion-dollar question.
It really is. Thank you so much for joining us on this deep dive. It's been an absolute pleasure unpacking this with you. Stay curious, keep questioning the world around you, and we will catch you next time.